Alright, this is part 2 of the series, Angular Resolution in our world. These are our two options. Again, the horizon is either optical or physical. We're either bringing the ground to eye level, or the eye is being brought to ground level. In the end, we will see how we can use the angular resolution limit to calculate a sphere with a radius of 3,959 to 3,978 miles. These are our assumptions again. Perspective changes with the observer. The objects do get smaller with distance. Small objects do disappear from vision, and the horizon rises to your eye level because it is an optical phenomenon. And the two surfaces above and below your eye line are roughly parallel. Again, our objectives defining the series. We're now on number 2, perspective changes with the observer. So if it's not apparent right now, the horizon rising to eye level is a very important piece to this, so it will become evident as we go on. So let's do some definitions here. With a one-point perspective view, which is how we see the world, the radial lines are called orthogonal lines, and the rectangular lines are transversal lines. And they are 90 degrees to one another when viewed orthographically in that top right diagram. Again, which is kind of a side view. So we've kind of outlined which ones would be transversal lines and which ones would be orthogonal lines. Objects placed in our field of view line up according to these lines. The horizon is our eye line, where the bottom 50% of our vision meets the top 50%, or the ceiling meets the floor, or the sky meets the ground, etc. It is also the vanishing line, and where it crosses our vertical orthogonal line is the vanishing point. It's always 90 degrees to our eye and comprised of all the information lost within a resolution angle of 1 arc minute for the human eye. The angle is situated plus or minus from 0 degrees. Again, you can see these rectangles as they descend, or as they move further away to your vanishing point, they get smaller and smaller, and the lines get closer and closer, but they still represent 10 feet. So to see how we have a horizon or a vanishing line as opposed to sometimes a vanishing point, we need to change our original corridor a bit. Keep in mind that these concepts aren't mutually exclusive. A vanishing point is present when there is a vanishing horizontal line or a horizon. In other words, if you just see a straight horizontal line, there is still a point there in the middle that things will ascend, let's say from the top down, they will ascend to that point vertically intersecting with your eye. And a horizontal vanishing line is present when you focus to a vanishing point, but it may not be apparent in the presence of tangible objects to your left or right. So again, in other words, there are these orthogonal lines that can be represented as the horizontal one is going to be basically the horizon line within a corridor. When you extend the walls away from you, that line becomes basically multiple points along a very distant orthogonal line, and that becomes your horizon. So hopefully that makes sense. If it doesn't right now, we'll continue to look at these diagrams. So consider that we are now looking down on a person's field of view axially, and we're going to alter the left wall, which is that yellow line, by rotating it away from us. So your view would change from this kind of corridor, if we were looking top down and looking into the corridor, to something like this, where the left wall is being rotated outward and away from us. The vanishing point is still there in the center where those two yellow lines are intersecting. But you can see how now the orthogonal lines are getting more and more shallow as they're rotating outward and away from us. And we can continue to rotate this wall outward and away, and eventually the orthogonal lines collapse into a horizon line. So our horizon, or our vanishing point, has become now a vanishing line. So the lines denoting the left upper and lower corners now converge to a single line as the wall rotates away from us. As it rotates, it gets further away, and eventually it will be the same angular size as the furthest objects within our perspective view, and it vanishes, leaving the floor and the ceiling visible. So hopefully that makes sense. If we now rotate the right wall 90 degrees away, we are left with a floor and a ceiling, and the left and right walls are compressed into the now horizontal vanishing line on both sides, left and right. So now in that bottom diagram, you can see that we are essentially left with basically a ceiling and a floor. We have no tangible physical walls obstructing our left and right visual fields, and we have a horizon. Now instead of the left wall, let's remove the ceiling. So I've just rotated, I've replaced the walls and put them back in, and we'll just rotate the previous wall to become it's now our ceiling. And now it rotates away from us 90 degrees, pivoting outward from our center view. So this is what we would see when there's no visible ceiling. We still have two walls and a floor. And now removing the floor, this is what we would see with no floor and no ceiling and only walls. It's essentially a vertical horizon, or you could suppose call it a horizon, but it's essentially your vertical vanishing line. So to clarify, if there were no objects on the walls and only perfect paint, this is what we would see. But as soon as we place an object there, we would perceive it according to a central vanishing point. In other words, right now it's a line, but there is a point on that line where it is perpendicular to our eye. And so at that point, that's still your vanishing point. If you put an object within that field, it will line up so that the orthogonal lines on that object would intersect at the vanishing point. So since massive walls are a rare sight, we'll focus on the horizontal plane, and we'll just rotate ourselves back again to where we have our horizon line. And let's now rotate the ceiling away from us, and we're only left with a floor and potential orthogonal lines and transversal lines and the vanishing point situated there. So now we place an object, and it will arrange itself according to that potential, those potential orthogonal and transversal lines, even though they may not be readily apparent. So any object placed on the floor that have depth, i.e. they travel any distance from near to far, will arrange themselves based on these potential orthogonal and transversal lines. This is essentially what is seen with no ceiling, walls, or floor, like you are in a giant room of white as far as the eye can see. The only thing you have are unseen potential field lines. If an object suddenly appears in front of you at a given distance or height, it would conform to these lines and line up according to that vanishing point. If you draw the orthogonal lines on an uncropped, non-distorted photo, you can determine this central vanishing point or the camera's center field of view within that frame. So now let's add back our walls and some objects to see how they look. If we add a floor and a ceiling, we get something like this. So we're starting to just kind of build back our corridor here and see how objects would align themselves when placed within these lines. If we add our right wall back again, an object would look like this along the right wall. So now we have something on the floor, something on the ceiling, something on the right wall, and something on the left wall now within our corridor. So we went from potential objects with no ceiling, no walls, to now objects with the walls in view, and you can kind of see how they would align themselves with or without the walls. Again, the objects are still there, but we've removed the walls and the ceiling now. Another way of seeing this is that these lines dictate how the world is viewed within our vision. So they're, again, potential lines that allow things to line up according to them. If a floor is placed below us, it conforms to these lines, but always within the lower 50% of our vision. So if I get closer down to the floor, more and more of the floor is taking up 50% of the vision, and it gets compressed. So again, if the ceiling is there, same thing, it conforms to these lines, and then that's how we see the world. So in this photograph below, we no longer have tangible, physically obstructing walls or a ceiling, yet our vision still contorts any non-uniform object along these lines. Although we have a vanishing line, you can see how the clouds are compressed along these lines to the vanishing point. So the clouds there are all descending away from you and converging towards that point. Something to keep in mind is that these crops, let's say, the crop maybe just to the left of that orange circle in the middle, that orange vanishing line, that crop is actually potentially miles to your left, or it could be a couple miles to your left. Same thing with the crop line that's maybe just a little bit to the right of the orange vanishing point. Again, as you spread this photograph outward, that crop line is actually potentially very far to your right. So when we place objects within our view, you can see how they move along these lines, like looking at an XYZ axis. Again, all these things are moving actually from you, straight away from you, but they all converge towards the middle. Objects with a lot of depth from near to far will appear to converge more toward the vanishing point according to the orthogonal lines along a z-axis, like a depth axis. Objects with only a little depth along your peripheral vision or objects directly in front of you align themselves at transversal lines or the XY axis. So again, I've kind of noted those here in the photograph. Again, a photograph or even your vision, how you look at things, it's just two-dimensional. But it's how you're perceiving a three-dimensional world, but it's just a two-dimensional picture. But the z-axis we can kind of denote as these orthogonal lines that are converging towards the center vanishing point, and the xy as the transversal lines, which are somewhat akin to those rectangles within our perspective view. And I've kind of outlined those below with this cement box here in the middle. You have xy axis along the front part of the rectangle denoting the cement box, and then along the part of the box that's extending away from you, the depth axis, you can see how it's converging along orthogonal lines towards the vanishing point. So adding all the lines in now, you can see the linear world in which we live. So you can see how the railroad tracks line up towards the vanishing point, and so on. So along that line, if we are looking at the depth, let's say if I remove the depth from an object, like say our boxes that we put along the ceiling and the floor and the wall, along my periphery, you can see the effect. It retains the XY dimension, and the Z dimension is essentially lost. It just becomes more or less a rectangle. So with this in mind, note as objects move away toward my vanishing point, their perceived depth is compressed more than their height or width are. So an example to kind of visualize this is a car is next to you on your left with a lot of depth to it. It's just starting out to your left, let's say on the freeway, and it's driving away from you in a straight line. Let's say it stays in the left lane all the way. The further the car drives away from you, the less you can see of the side of the car, and eventually you'll only be able to see the tail end. So its depth got compressed, but you're still seeing the tail end of the car. It will appear to move right as it moves toward your vanishing point, but in reality it's always to your left in that left lane, moving away in a straight line. It's just how your vision works. So we now know some of the issues translating the tangible physical world to our visual world. Let's now move the eye or aperture height of the observer so that we are no longer perfectly positioned in the center of the corridor. We see that our angles now change in our orthographic side-on view. you can see that the angles that are down towards the floor have gotten smaller, and the angles up towards the ceiling have gotten bigger. As our angles change, the information at the top is now expanded above our eye line, and the information below is now compressed. If we add our paint back to our hallway, you can see the angle differences for the same 10 feet worth of information. 10 feet below our eye line no longer represents the same 10 feet above. So our converging model, where we rotated the ceiling and the floor up to the vanishing point in the center, it looks a little bit different now when we lower our eye height. So as we lower our height, the angle at which the floor meets the ceiling is different now. It gets bigger because the ceiling is coming in at a steeper angle. So again, if I lower my eye height now relative to the same corridor, if I just get lower down to the floor and then I rotate those 2 points down to meet one another, the point at which they meet is going to be a wider angle, because the floor or the ceiling is coming in a little bit steeper and the floor is coming up a little more shallow. So the ceiling meets the floor a little bit sooner when this happens, and this is why when we lower our eye height we can't see as far, and conversely when we raise our eye height we can see further because these angles change, and it has to do with the compression of these angles. Look at the lower left diagram there, and those blue angles, how compressed they are when we lowered our eye height. And again, you can model this for yourself with software you're choosing. Just line up these lines and have them connected to a line, and you can move the eye if it's connected to these lines as well, up and down, and you will see how the angles get compressed and expanded relative to your eye position. So this will be more apparent as we go on, but essentially your horizon moves in further or moves in nearer when you lower your eye line, and it extends out further when you raise your eye line. And the information lost within this gap here, this orange gap that I've kind of outlined between the two vanishing points, represents what is lost when we lower our eye line and our vanishing point arrives sooner from those greater floor angle compressions. And the amount of distance lost is proportional to the height loss in a linear relationship. So recall that height was proportional to 1 over the distance, or that height 1 over height 2 is equal to distance 2 over distance 1. So again, height we're calling in feet here, but in distance in miles. So example, if we're 6 feet up and a boat is traveling away from us and disappears at 3 miles, a rise in elevation of 12 feet to 18 feet up would represent a 200% gain, and we would extend the horizon 200% to 9 miles. The parts of the boat differentially compressed by the height change would be visible again. And this isn't because you're seeing over a curve, it's just because you can resolve more information with resolution angles that are no longer as compressed. So there's plenty of times where people have filmed a boat heading off into the distance, like a cruise ship or something like that, and then they view it a certain way with a certain amount of cutoff, which we'll get to as to why it's cut off, but then they extend themselves up maybe 30 feet or so to view it again, and then they can view more of it. But this isn't because you went over and saw something over a curve. You're not tilting your camera down to see it again. It's just because you've decompressed those lower visual angles, and you've resolved the item again. You've extended your horizon a little bit further, so you can resolve more within your visual field. So continuing on with the differential rate of information loss, you can see the effect here with these bottles. The horizon is set by the observer height again. So as an example, if you can see 9 foot down this table at a 3-inch elevation above it, and then you lower yourself down to 2 inches above the table, your lower horizon is now closer by 33%, or it's now at 6 feet in. You can't see as far down this table. The detail is lost. Essentially, your horizon is brought inward, and this represents the new lower horizon line. So the rate of descent along the tops of the bottles is greater than the rate of ascent along the bottom. The compression rate is higher along the bottom, and the angles are more open along the top. Things will appear to descend above your eye line at a faster rate than things are ascending below. Therefore, things below our eye line will appear somewhat stabilized in relation to those things above. As we'll see, if information continually moves into a narrower and narrower angle, eventually the lower part of the bottle will be unresolved while the top still remains. If I were to extend these bottles along a very long table, the bottom would disappear first with the lowered observer height, yet the top would still remain. And if I extend the table even further, the entire bottle will vanish when the top of the bottle descends below the lower horizon line. And that won't be apparent just yet, but we will go through that and illustrate how that happens. But just within this example right here, you can see how if you were to, let's say, view a boat descending away from you at that lower visual angle, and then you went up to a little bit higher, like on the left diagram, to view the boat, your horizon has extended. That table has gotten longer within your field of view, and you can now resolve more information just by raising height along a flat surface. So the lower horizon moves closer in when we lower our eye height. Note that we cannot see the horizon gain or loss along the z-axis with this perspective view. So you can't see that the horizon has gotten further away from you because it's extending and further away from you in a straight line. The vanishing point is the same point in both representations. But when you model these same angles as representative of the compression rate change orthographically from a side-on view, you see the horizon change along the z-axis. So again, I've just kind of used these same angles as more of a representation, illustrative representation of how the horizon may change with distance. It will be the same essentially as the height change. The amount by which the floor angle compressed is proportional to the distance lost. So again, the rate at which we lower our eye height is the same rate by which we approach the angular resolution limit with a lowered height, which we'll get to. So dropping our height by 50% means we approach that vanishing point 50% faster. So the horizon is brought 50% closer. So I'm just trying to represent that diagrammatically here, but essentially the bottom line is we are representing height in feet and we're representing distance in miles, but height 1 over height 2 is equal to distance 2 over distance 1. So as an example, a bottle on the street was filmed 107 feet away at different heights, one being very low to the ground, one being higher up. When the camera is lowered, the bottom gets cut off. The bottom compressed essentially until the information vanished. Again, this happened along a straight road. With the higher viewing angle, the object comes back into view in entirety. Video link is in the description. So as we'll see, this vanishing point is the angular resolution being breached for the observer. And so if this point is unknown, if this angle essentially is unknown, you can calculate the angle by using the amount of the object that is being cut off at a known distance. So we'll return to that after we discuss angular resolution limit. But again, the bottom line here is that when we have our higher observer height, the bottom can be seen. As we lower ourselves down to the floor and the floor is taking up that same 50% of our vision, we are resolving less and less detail of this object at smaller and smaller angles, and there's a certain angle at which the information is simply too compressed and it cannot be distinguished and given context as an image, and it will disappear. So as we'll see, the loss of information is a function of angular resolution and perspective, not curvature. So here's another example. If you look up an extremely tall building with a narrow viewing angle by getting very, very close to the building and looking up, a person beyond the vanishing line at the tallest floors could wave a flag out the window and they wouldn't be seen. And you can see the that the side of the building becomes so compressed that the top floors become indistinct in these photos. So you can see how the floors are somewhat distinguishable lower down in your eye, but as they get higher up, they become merged and they are very difficult to distinguish from one another. If these buildings were a little bit taller or the person was standing a little bit closer in, the top floors and anything sticking out of them aren't observed. So if someone were outside washing windows and they ascended to the top floors beyond your vanishing line, they would disappear building side first as they appear to set into the building. But again, the building isn't curved. This is just a function of perspective and the angular compression of information. So these buildings are just examples here in this photos. They need to be actually a little bit taller, or the photos taken a little bit closer in, or done with a smaller aperture camera like an iPhone or something like that for us to lose the top floors a little bit sooner. Here's another example of the observer height effect when lowering or raising your iPhone to view a flashlight on a very long floor like a supermarket. The flashlight, if it's low to the floor, disappears due to the limited viewing angle. Again, recalling from the optics of lens systems that we need those two diverging rays to extend through f1 prime and f1 and reconvene and cross to create an image on the back of your retina. Same thing occurs with a camera. These two light rays must diverge and then get reconverged again to create that contextual image. So raising the flashlight carries the same implications as lowering the eye height. The light is shining parallel to your position, but you cannot see it because of the camera aperture angular resolution limit. Again, video link in the description. But here this person is doing this experiment on a long floor. Here the light is about 8 inches off the floor and is visible, which is in the middle of that circle, yellow circle there. And as he lowers the light down, it disappears. And again, you can do this with any iPhone on a flat surface, and as long as your camera lens is side down, you can view this kind of essentially setting an object below your horizon line. Again, that floor is taking up 50% of your vision, and the detail is lost beyond your vanishing line. Anything setting or getting placed down below that vanishing line is going to disappear. So here the light on the right, it's lowered down and placed on the ground about 1 centimeter off the ground, and it disappears. But again, it's shining a light essentially directly parallel to your position. But again, you've kind of set this light like a mini sun. So we'll continue going through this, but I hope I explained the altered height within perspective when viewing fixed objects. Let's now see how moving objects within a fixed perspective are observed. We'll return to our center eyeline view. We'll keep all things equal and look straight on at an object. If it's directly in front of me and I just move backward or move the object further away, it maintains its proportions from left to right, top to bottom, and just gets smaller. Just like the transversal lines, which are the rectangles, these orange and blue rectangles. I just took some of these out and modeled them as they are become essentially a moving object, moving straight away. So here's our object. It's coming toward us. It's getting bigger, getting smaller, getting smaller, getting smaller. If we have an object to our left, so again, in that previous example, the object was straight in the middle of our eye line, and we were straight in the middle of that corridor. But now if the object's to our left and is sufficient size to have aspects above our eye line, you see that the top moves inward along the top orthogonal lines, the bottom moves along the bottom ones, and the compression expansion rate is the same between the top and the bottom halves, but because it started out to our left, it will always remain to our left. But again, it will just move along those ascending and descending orthogonal lines. Here it is coming out towards us. and it's going back again along those orthogonal lines. Now let's see what happens with moving objects that are not directly in front of you, nor centered on our horizon, our eye line. So in this case, we'll assume our moving object started out to our left and below our eye line. If I maintain my eye height and the object moves away or straight away, it will appear to converge towards the vanishing point. So our object on the floor appears to rise and move to our right. But again, it is moving straight away from us along the floor. Note that because the object started out completely below our eye line and to our left, it always remains below our eye line and to our left. It will diminish in size according to those field lines set by our observer position relative to the floor, wall, and ceiling. So again, the orthogonal lines will be dictated by our observer position. In this case, we're still in the center of a corridor. So the ascending and descending rates are essentially the same, but we now have an object that is below our eye line and situated off to our left. As it moves away from us, it will always remain down below our eye line and to our left. And before moving on, just keep in mind that with our eye line moved lower, the building, let's say in this example, still maintains its proportions relative to itself. Or let's say it's the bottle. If we pull out a rectangle like the green or yellow ones from both perspectives, they are still the same rectangle or square. They have the same dimensions. But the position has changed relative to the observer. And as you can see, our eye line is no longer centrally located within the object. It's now lower. So the purple line, when we move our eye height down within perspective, it becomes lower along that object. As the object gets further away, it still diminishes in size the same way, but it does so at a different rate from top to bottom. So also note along that bottom view, when we lowered our eye height, we compressed those lower transversal lines. Note how they got compressed and they got closer and closer together, whereas the ones above got wider and further apart. So with the lowered eye height, we can see that if an object starts out below our eye line, it still remains there throughout and maintains its relative proportions to itself. So again, these boxes or rectangles or whatever you want to say, you can put them in any position. They will continue on in proportion linearly, right? And remembering that height is inversely proportional to 1 over the distance. Now we'll extend the object height so that it starts out with some aspects above our eye line, but most of it below and slightly off center. So as the object gets further and further away, the aspects above the eye line will compress at a differential rate to the aspects below. It will appear to be a more dramatic change at the bottom, because more of the bottom of the object was below the eye line to begin with. Just take some of these rectangles out again and stratify them along any orthogonal lines to see this effect. So again, I've pulled out the rectangles. I've just color-coded them gray now with blue outlines, and I've stratified them along different orthogonal lines. In this case, I just chose 2 black orthogonal lines and placed the rectangles, lined up the corners of the rectangles, moving away from you towards your vanishing point. Let's reverse things now with most of the object above our eye line. So before it was mostly below, now it's mostly above. Like let's say if we were 6 feet off the water and looking at a large boat that was 18, 20 feet high traveling away from us. So again, our eye line would take up only about 6 feet worth of the bottom of that boat, and the remaining 12 to 20 feet would be above our eye line. So if you look closely at the diagram, you'll see that the bottom of the object is approaching the vanishing line or horizon. So those transversal lines get very close to that horizon line very quickly. So in essence, what ends up happening is the bottom becomes less distinct earlier than the top. And so that's kind of the takeaway from this point. And if we go back to our boat example, the bottom 6 feet that were below the eye line, since we have a 6-foot observer, they're going to become less distinguishable and more merged than the top of the boat will as it moves away from us. So you can see I kind of blew up what's happening in the center portion of this image diagram, and you can just see how below that purple line, the blue lines are very merged with one another, very hard to distinguish, but you can still make out the rectangles above that purple line very easily. So as we'll see, the compressed angles below the eye line have proportionally expanded paired angles above. So as I compress one on the bottom, I expand one at the top at the same rate. So also for exceedingly tall objects, the aspects below the eye line are negligible in comparison to their total height. So they stratify along the horizon line essentially. So if I'm looking at a 1,300-foot object or a 13,000-foot object and I'm only 6 feet high, the aspects that are below my eye line are essentially negligible, and you could essentially model it along the horizontal line. And they are going to then descend at a rate commensurate with their pairing below the eye line. So if close to the ground, the descent rate is steep. If I'm higher up, it's more shallow or gradual. These mountains would represent the same height if I observed them in a side-on orthographic representation. Keep that in mind. They are seen here, however, in a one-point perspective on the bottom diagram, and they therefore diminish in size. I could replace the 4,000-foot mountain, let's say, with a 4-foot car parked at different distances, but it would be the same phenomenon. I would just be lower to the ground relative to the car to view it this way. The rate at which they diminish is linear within a fixed perspective. So again, my eye line would just have to be very close to the bottom of the tire on against the car for me to view it this way, but it would still descend away from my vision the same way. Just like if I were to stand straight up and look at this mountain, it would descend according to its paired lower visual angle of a 6-foot observer along that orthogonal line. But we can reverse some of the near and far objects, keeping them according to their transversal lines, and we start to see a typical panorama form with 6 equally sized mountains. The 3 on the left are in a straight line, but they converge right. The 3 on the right are not in a straight line and have the same heights at the same distances. So again, the ones on the left I've essentially modeled as they started out on your left, let's say, and they moved away from you in a straight line away, and that's how they would be viewed. And the ones on the right are just kind of situated, maybe starting out on your right, but then moving away from you in not in a straight line, moving even more to your right, and that's how they would somewhat appear. And we can add in some different mountain heights here and there, and add in some clouds, and then stratify them again along these orthogonal lines that we would have to figure out according to our eye height as to how they would stratify. And this is essentially how you see the world. This is your perspective. So to summarize, the lens converges light rays that expand from a source according to the inverse square law by a proportional amount. The rays with which we view an object have different angles depending on the presence of an obstruction like the ground, ceiling, or walls. So again, if I lower my eye height, I am viewing things at different orthogonal lines. The information above and below or on either side of the eye line are paired. As one angle opens, the other compresses. With a lowered eye height, the ascent rate decreases below our eye line, and the descent rate increases above our eye line by a corresponding amount. And we quantified this phenomenon as h1 over h2 equals d2 over d1. The amount by which we lower our observer height is directly proportional to the amount by which we bring the lower horizon closer, and vice versa. If the lower horizon is closer with lowered height, once that distance is met by the descending information above our eye line, things will set into the lower eye line with further distance. So with that understanding, let's now take a deeper look at the angular resolution limit in the next video. Recall our lens system. We will now complete the picture and add in the bottom of the tree now. So we have our f1 and f1 prime up in front of and behind our lens. Our tree is moving away from us to the left in this diagram and getting smaller and smaller with distance as it is trying to create those crossing points behind the focal point and projecting them onto the retina. As the image continues to get further away, the angle of resolution across f1 gets smaller and smaller until about 0.02 to 0.03 degrees, or 1 arc minute for the human eye. This is the point that the cones in our retina can no longer resolve the image because the light rays are too close. In other words, we've met our vanishing point. This is the visual acuity of the average person taken from the central portion of the back of the retina where our rods and cones are most concentrated, which is the fovea. Light hitting the fovea at less than 0.02 to 0.03 degrees cannot be distinguished from other points of light, and it is too compressed, as we'll see. More specifically, it is the point that 2 light rays diffract to a point of 50% overlap. So 6 rays become 3, 4 become 2, and 2 become 1. An image cannot form with 1 ray. It needs the other to create the inversion. No image forms at this point. So with the broader concept in mind, let's look at the diffraction limit in the next video. Again, thanks to everyone who's working on cracking these issues. And again, for the next video, we will discuss angular resolution, Airy patterns, Airy disks, Rayleigh's criteria, and the diffraction limit, differential angular compression, and the resolution of images above and below the vanishing line, angular size, stability of the sun and moon, the cause of the sunset, the importance of Polaris with regard to distant vision and position, and the effects of magnification on perspective and the diffraction limit. And hopefully within this video we discuss perspective changes with the observer, mainly observing that with lowered eye height that we started to compress the information within the lower 50% of our vision to a point where it became non-distinct.